had time, I pulled it up. But right now, we'll call it forever 11 in case, well, what was the last forever that we had? All the basic rules, right?
What did you say it was?
Was there anything after the basic rules? That's the last one I have. Does anybody else have any others? Okay, so we'll call this one 11. Or it is number 11, maybe I should just put it that way. Okay, forever number 11. What do we have? We have that the position function could be called S or X. We have velocity is called V. But there are two different ways of finding velocity. Remember, velocity has magnitude and direction. Positive, negative velocity indicates which way we're moving, like whether we're moving right or left or up or down. Average velocity, we're doing a slope. Change in y over change in x between two times. So t is a to t is b. And I think a couple of you asked this last week. I think I switched something up at one point. We do always do the latter minus the earlier, or a physics person, final minus initial, right? Final minus initial. So what happened later minus what happened earlier. We do always do it in that order, which is why the b comes first and the a comes second. Instantaneous. What's the illustration I used last week for instantaneous? Trying to figure out how fast at an instant. The radar gun. Good. The motorcycle cop. True. So the radar gun, trying to figure out how fast you're going at one time. If you're plugging in one time, this formula can't work. One time, what do I need? The derivative. And velocity is the derivative of, aka the rate of position. What's going on with speed? Why does it have absolute value bars?
Because negative velocity is positive speed.
Yeah, speed is always positive speed. It's just the magnitude regardless of direction. And then acceleration, we didn't really talk about. We haven't really talked about a lot, but long story short, I did say it last week at some point. Acceleration is speedometer speed, aka like velocity without sign. Speed is how fast. Speed is how fast your position is changing, aka in some senses how fast things are moving by your window as you're driving, right? Acceleration is how fast the needle is moving on your speedometer. So what speed you're going shows how fast things are moving. Here's where the rate of change is. It's your position that's changing. Acceleration says how quickly is your speed changing in some ways, shapes, or forms. So if we're trying to find acceleration, then we need to do the velocity prime, which is the same thing as take another derivative. Here's our introduction to more than one derivative. Take another derivative of position. So take the derivative of position once and take it again. We talked Friday about hitting the ground. All we know when you hit the ground is that your position is 0 because you are at the ground. And once again, in physics, you kind of define things differently. You could make the building the ground, and then all of a sudden you're at negative height. Like, it's very subjective as to how you model it if it's not given for you. But for us, for the most part, when you hit the ground, we're going to say your height is 0, your position is 0. For free-falling objects. For objects that might be propelled initially, but then they just go with gravity after that. Initial, actually in all motion problems, initial, we're always going to say that t equals 0, what's happening at the very beginning. Unless stated otherwise. But if it's just a clue that's given to us and they don't give us any beginning times, we're going to say time is 0. And then if something is dropped, is it being propelled? No, it's just being let go. So if it's being let go, there is no force behind it as far as it being dropped with an initial velocity. So we say the initial velocity is just 0. But this does not necessarily prepare you for some of the problems in homework where, for those of you guys that attempted them. Did homework talk about gravity at all?
I hope so.
You hope so. It did! Yay! Go team! Alright, anyway, let's go ahead and go look at the book. You guys scare me sometimes. Ebook. Section 2.2. If you have your book, you can open it up. If not, we're just going to peek at it together. We're not going to do all of them. However, section 2.2, let's go to 2.3 and go backwards. Word problems. Ooh, look, word problems. What homework did you guys have in 2.2? You had 89 through the 90s and 102. Okay, so homework started here. Number 89. We're not going to solve it because you guys don't seem to be ready today. Some of you were, and that's good, but let's just talk through a few of the directions. Okay, what are the directions in number 89? Pause. Do we have a formula for that in forever number 11? Yes, average rate of change is S of, wait, we don't have an S, we have a type. It's still our position function. So instead of being S of B minus S of A all over B minus A, how are we going to plug into this one? F of, which is 2 minus F of all over. Yeah, we're just going to plug in Chuck. And, ooh, it's a pink one. Remember, scan the QR code in your CalcAB app and you can watch the video of someone explaining it. That was the beginning, but then after number 89, I do believe pretty quickly, 95 to 98, I go to words. So, what are the directions for 95? No, 95. Use the position function. Did they give me an equation? Yes, but what's missing? Now hold on, we kind of wrote it in our Federal card. What's V sub 0, aka V sub naught? What's that stand for? Initial velocity. So, number 95, when it says a coin drops, what are you going to say initial velocity is? 0. See, you have to make our connection. They're not going to tell you V sub naught equals. So, a coin drops, V sub naught is 0. From the top of a, wait, what do you think S sub naught is? If this is initial velocity, what's this one?
Positive, or you can set it equal to 0.
Yeah, like initial position.
It's probably easier to set it equal to 0.
So what equal to 0? Oh, and have negative 1362 to the ground? It's getting too physicsy. So we'll go ahead and say initial position or initial height is going to be our 1362 because that's where the coin starts from. So once again, you're at a railing, you're on the edge of the building, and you're dropping it. Okay? What? Yeah, plus, because it's up. If it was like a hole, then it'd be, well, I guess you'd have to be shooting it up.
Yeah.
Anyway, you know what I mean. What Tyler was saying is sometimes in physics you just make where it starts 0, so then it would be going at negative height, but we're just going to go ahead and say the ground is 0 and say 1362 is the initial height. So wait, do we already have this one?
Yes.
Plug in 0, plug in 1362. Done. How are we going to find velocity?
Just plug in for
derivative. The derivative. Now, there might be a formula that you have because you know a constant acceleration law, but that would be the same thing if you think about it as the derivative. Bring down the 2, negative 32 t plus initial velocity, right? Okay, so then moving on, you're going to solve for some different functions. Let's go ahead and peek at just a couple more. What do we have? 95 to 98? Ooh, all of them. Well, 95 and 96 are pretty similar. What's different in number 96 since it's an even? You're still using the same equation. But what's different? So V sub naught? Not 0. V sub naught is negative 22 because the ball is thrown down. Much different than being dropped, right? If you drop a baseball, if you throw a baseball, one's going to hurt a whole lot more if you get hit by it. All right, we have 97, 98. What's different in this equation? Ooh, Tyler, why is it negative 4.9 instead of negative 16?
Oh, thank goodness, we're using 9.8 for gravity.
This one's measured in meters and not in feet. Both of these equations are based on gravity because objects are free falling, and so gravity is the acceleration, long story short. And if you're in feet, it's negative 32 feet per second squared, which is where half of that is the negative 16, but in meters per second squared, it's negative 9.8, which cut in half is negative 4.9. Anyway, no big stress except your units have changed. Make sure you were aware of that. But otherwise, isn't the formula the same besides that number right there? Yeah. So everything you can still think of basically to be the same. You're going to have to think a little bit deeply because number 98 does not give you a lot of information. But if you have a building, you don't know how high it is, you might have to like name it H or something, which is the same thing as the initial height or the initial position. So you might have to make that a variable. But if it's going into a pool of water, what's going on when you see the splash? What could you say the height is if the pool is at ground level? Yeah. You could say the splash is when the height is 0. Alright, so we have a few word problems you guys are going to think through if you have not yet already, but then you only have 2 more problems after that. So get through those 4, do the best you can, write down the important information, try to solve. 99 and 102, and then you're done. So number 99 and 102 are both graphs. What are the directions in 99 and 100? What's the graph of?
It represents the distance.
Which is the same thing. What's our snazzy term for distance? Position. So 99 and 100 are position graphs. Look at 101, 102. What kind of graphs are they? Velocity graphs. So 99 and 100 are like the graph of f. 101 and 102 are like the graph of f prime. Have we been introduced a little bit to how to deal with graphs of f thinking f prime or f prime thinking f?
Yeah, you just
A little
get
bit.
lines, something like that.
Yeah, a little bit. So let's look at 100. There's 99. Well, you guys have to think through that one. Let's look at 100. It says make a sketch of the corresponding velocity function. So velocity is the same thing as graphically slope, right? Can we figure out the slope if we have 2 points on a line?
Yes.
Okay. So what would be the slope between 0, 0, and 6, 5? You rise 5, and then you run 6. So we can say that the slope here, if we'll make it right, that's lame. The slope is 5, 6, and then the slope is 0, and then the slope is, from 5 to 6 is 1, and from 8 to 10 is 2. The slope is 1/2. So if I was to think about how to sketch the graph of, that's going to be in there, hold on.
Flat line. You're not accelerating, so flat line. 5, 6.
This button not work. Oh, it doesn't work.
Everything's malfunction.
That's about right. Okay. So we were able to see that this slope,
That's malfunction. Calibrate.
this slope, I know, is 5, 6.
It's fun to watch.
This slope is 0. And this slope is 1/2. And I was only able to do that because these are linear. I was having too much fun on that one. But then if I go to graph 5, 6, well guys, hold on, I've been graphing velocity for all of these times between 0 and 5. I need to actually, or between 0 and 6, I need to actually have 5, 6 be the value. Isn't that just going to be a straight line?
Mm-hmm.
I'm going to have 5, 6 be a little bit below 2. And then go all the way to 6. Now, why am I going to go ahead and hold on, I didn't calibrate? That's annoying. Can't do it anymore. I tried. That didn't help. Patience is a virtue. You're right.
What's the point of dragging it?
Theoretically, if you just tap on it, you're going to be in different places, but if you drag, you can get more to the center. Does that make sense? Yeah, people come train us on the smartboard.
We should go back to chalkboard. Of course, it's
So
gonna
people
be.
come train us on a smartboard, like one of their presenter people's. Anyway, so she puts in drawings, and now we all do it. Well, I don't know about that's all.
Only you.
One of us is left. 2. You're right. 2 of us are left in that time. All right. So I'm gonna have 5, 6. Why did I write a hole at 6?
Because at 6, it's going 0.
At 6, it's also going 0, but
It's still
it's more than that. Why would the derivative not be able to exist at 6?
It's a breach.
Sharp point. The slope from one to the other, they clash. This one says it should be 0, this one says it should be 5, 6, and every derivative is a limit, and the limits must agree to exist. And if they don't agree, they don't exist. Same thing here. Aren't they clashing? Doesn't this one say 0 and that one say 1/2? So therefore, once again, okay, well, sorry, because 1/2 and 5, 6 look very close, and they aren't, but not that close. Anyway, and they both look like they're above 1. Anyways, long story short, it's going to be a flat line at 5, 6, a flat line at 0, and a flat line at 1/2. And I have to make sure there are holes at all the sharp points. Technically, this one's only a one-sided limit, because it's only coming from one side, which is why I filled in both of the endpoints. Because one-sided limits can agree, but if you have 2 sides and they disagree, we have to say the end. Okay, so that's number 100, and number 99 is going to be very similar. 101 and 102. I don't remember what I gave you. Oh, and I just closed it. Lame sauce. I feel like I would have given you 102, but maybe it would have been nice and given you 101.
It's on the front.
Okay. So number 101, we talked about how it's different because it's given velocity and not given position. So how would we find the position function? Now we're working backwards.
Slope is 40.
So now we're trying to do position. Hold on, let's look at the directions really quickly. It represents the velocity in miles per hour during a 10-minute trip to work. Make a sketch of the corresponding position function. Do you guys remember if we're going from derivatives backwards, do we know exactly where to put it? Not exactly. We know the shape. We can know the shape, but we won't know exactly where to put it unless they give us a point. They have to give us like a starting point. I'm going to go ahead and close this really quickly because we're done with it. So I am going to tell you we are going to get the basic graph, but we're not going to necessarily know exactly where to start. If you want, I guess you could for right now, since they didn't tell you anything, I should say. I guess you could assume that when time equals 0, you start at 0. No, but what if you start at your house on your 10-minute trip? Doesn't matter. Can't you make that the 0 and then everything is how far away from that? So I guess we could, since they didn't tell us anything, I guess we could say at 0, you start at 0. That's your position. You're at the beginning. Wherever you are, we'll make it position 0. Okay, so Tyler, you said the rate is 40. What does that tell me?
Slope of the line is 40.
So as I rise 40, I need to run 1. Right? And how long is the rise 40?
Until 6 minutes.
I think. So 6 would be like what, 240?
Oh gosh.
We'll just do that.
Sure.
Pretend it's straight.
Of course now. Oh, it has to end at 6.
Yeah, it has to end at 6. Oh, was that my 6? That was my 6.
Yeah.
Okay.
And what is your any other new problem?
There is a gap. Which means what?
Well, v equals 0, so you're just
The
going to
slope was 0, your rate was 0, you were stopped at a stoplight or a stop sign. Does that make sense?
2 minutes.
So you were going 40 miles per hour. Hopefully you gradually got up to that. But anyway, so you were going 40 miles per hour, then you're going 0, so you're stopped. So what's going to happen to my position? Do I change position if I'm stopped?
No.
So what am I going to do? Stay at that position. Just like up here, right? I'm going to stay at that position. Then what?
We're going to go 60.
Now I'm going 60. Oh, I struggle. Make it a little steeper. I don't know. Anyway, so, and then here, we should have stopped. But do you guys see what I'm doing? Go up 40 over 1, up 40 over 1 for the first 6, and then all of a sudden you're stopped because you can't see it, so it must be on the axis. You're stopped, so it's flat, and then all of a sudden you're going even faster, so the slope is even steeper. That would be a position function. We'll call that ST or axis. Alright, kiddos, we have introduced motion officially. We have not covered it. We have not fully grasped motion or even delved into the depths of motion, but we have introduced it. It is going to be coming back a little bit later on this chapter, so don't worry in case you were worried. It definitely is coming back, but for right now, that is as much of an introduction as we're going to do. So you guys work on that homework for tomorrow if you have not yet. The sad thing is I totally had like a warm-up for us to do, but I noticed very quickly that many of us were not ready. So we're going to save that workspace multiple choice practice for the very first thing tomorrow. We have 3 multiple choices. So go ahead and finish up that homework and we'll see if you can ace the workspace. Come with your questions. But we do need to start section 2.3, which is a nice thing because it's not an application. It's more basic. They're harder. They're more involved. You did see, I think, both of them this summer for a little bit. Product quotient. You guys see a little bit?
Yay! Yeah.
Product quotient. You have seen them. We are going to get forever cards on them. Tomorrow, after we finish the motion homework, which we were supposed to do today, but oh well. Tomorrow, after we finish going over the motion homework, we'll get our whiteboards out and in our groups try again. See how we do with competing on these formulas. So if you can practice them a little bit tonight on your own. You guys know how using the rules last time went. Maybe you want a little more practice before we compete. I have not given you these rules this year yet. I have not had you make a forever card, or I have not made you memorize them yet. So how would you how would you need to derive this without the product rule? Tyler's right. Do you guys hear? Mm-hmm. If this was one of those from the basic derivative rules, this technically is all we have right now. You would have to rewrite, you would have to FOIL first before you could take the derivative. Remember, ddx, that's Leibniz notation, FOIL is derived. Quick shout out to him every time we use it. 2x squared times 3x would be 6x cubed. Double check my foiling. You guys think? I like doing them in descending order. But I think this is also my first outer inner last this time. Can't combine anything because they're all different. The reason they're different is you had a squared in this and a single in that. Binomial times quadratic times a linear. But I'm not done yet. What was the whole point? Find the derivative. Since I'm using Leibniz notation, I'll go ahead and put dy dx again. You guys have gotten good at them, right? What's the derivative? Ready, set, just read it off.
18x squared. 28 plus 1.
98.
Plus 1? Plus 3. Where did I get plus 1?
That's going to be 2.
In my,
Yeah, that's a 2.
Sorry. That's where I got. Plus 3.
Minus
0.
0. The root constant is 0. So I have my derivative. Now, what if I wanted you to factor said derivative? Let's say I wanted you to find the zeros of the derivative. Wait, what homework problem recently wanted the zeros of a derivative? Horizontal tangent lines. Wasn't that a homework problem? Horizontal tangent lines, the slope is 0, so we set the derivative equal to 0. So what if we needed to factor to set it equal to 0 and solve for the horizontal tangents? That would be right. So come on, we're in calculus, we need to have a factor. Divide by 3? Goes into everything but 28.
You just have to break it out and multiply by 18.
You can break it down. You can do an X method, or you can do something like thinking of 1 and 18 and 1 and 3. That'd be 18 and 3. That does not make 28.
Use multiply 18 and 3.
We do 2 and 9 and 1 and 3. 9 and 6, that doesn't work. How about 3 and 1? 27 and 2? No. What's something else that goes in 18 besides 18 and 1 and 2 and 9?
Not much.
36.
9 and 6? No. 18 and 3? Uh-oh. Does it factor? No, maybe not. So, that wouldn't work. If you guys were like, how would I know for sure? Remember, you can always take your X method off to the side. 3 and 18 is 54, right? Factors of 54, 1 and 54, 2 and 27, 3 and 18, 4 doesn't go in, 5 doesn't go in, 6 and 9, none of those make 28, so it's impossible to make it 28. Oops, that's a big It's impossible to make a negative 28, so the only way that you could solve for the zeros would be to
Do some.
okay, you can do the quadratic formula if you like the quadratic formula, or you could complete the square. Or maybe be a calculator problem because it might be a decimal answer. Either way, we do have our final answer of 18x squared minus 28x plus 3. Did it work? Yes. Did we solve for it? Yeah. Is there another way? And the answer is yes. So let's go ahead and talk about the product rule. And sometimes the only way is the product rule. I'll show you an example in just a second. The last one we were able to do without the product rule. And we'll check it with the product rule and see if we're right. There are a few different ways of doing it. One way is strictly with function notation. One way is strictly with words, well, mostly. And one way is with symbols, because just a few of you, the symbols work a little bit better than anything else. So, technically, this rule could show up different ways. I go ahead and say second d first means the derivative of the first, plus first d second Now, ironically, if you guys think about it, this is just addition. So even though I do second d first plus first d second, the reason I do that is because I'm going to say the quotient rule in a very similar way, but with a minus instead and with a division. So I go ahead and try to make them sound the same so it's easier to remember. But if the book does, which it usually will, first d second plus second d first, are they still technically right? Can you switch this addition and it's still true? Yeah. So it doesn't matter. Technically, we could even do f prime g plus g prime f, but sometimes when you solve that way, you mess things up a bit. So that is the rule and function notation in words. If you think about two different functions, I'm going to show that with separation. So I have the first and I have the second. That's what the notation down below means. This one is my second. This one is my first. Still a shortcut, I don't want to get too much beyond that, but you could say the product of one function times the derivative of the other plus the other function times the derivative of the other. But it is going to be a little bit easier if you just think of it, keep the second the same, derive the first function, plus keep the first the same times the derivative of the second function. So each time you're only taking the derivative of one. Your brains naturally would just say, take the derivative of f, take the derivative of g, and multiply, but that is very, very wrong. And you'll see why in just a second. And the other notation, if you think about it, we'll do second times first.
Oh.
I have my moment.
No, he would use
Ideological. Plus
count.
first.
Yeah, count.
Guess where we got that from?
No.
I taught Algebra 1, and I showed it to them and said, F of count.
Yeah, I gotta beat that.
So I was like, I think this is good for their visualization. I was like, I like it, I want it.
Wow.
Just a little circle icon.
That's how we learned first learned after that.
It's a great way to learn alphabets. It's a great way to learn alphabets. That's how my college professor taught it, ironically. Yeah. Where's my thing? Oh, the air is not yet finished. On Mondays? Look at those. I want you to try to use the rule of the example we just did. Go back and solve it the product rule way. Go back and solve it the product rule way, cool kids. The function that we just did. Go back and solve it the product rule way.
I did.
Go team. Everybody else. I'm going back to the example that we just did. So we can solve it in alternative ways. So now with the product rule. You just put it underneath the product rule. It doesn't necessarily need to be back here. I just happen to leave room. If you like the boxing and the triangling, there's our first function. There's our second function. So when we're going to go find the derivative, you don't need to rewrite. You go straight to dy dx equals and. Second. A little troublemakers. Second d first. What's the derivative of 2x squared plus 1?
It's just 4x.
4x plus 0. Just 4x, right? Second d first. Derivative of 2x squared is 4x. Derivative of 1 is 0. Plus first d second. What's the derivative of 3x minus 7? 3. Oh, those don't look anything alike. Hold on, what would you do to make them match?
Just kind of slide in.
Yeah, distribute stuff, right? So 4x times 3x will just be 12x squared. Minus 28x plus 6x squared plus 3. Doesn't this indeed end up being 18x squared minus 28x plus 3? Did product rule work? Yes. And for those of you guys that like it, we did second, d first, plus first, d second. Do you need to be good at taking derivatives fast? Yes. That would be helpful. Now I said just a second ago, product rule in this one, it was totally an option. You could have FOILed and then derived like we did, the old-fashioned way, or you could have used the product rule and it should have gotten you to the exact same place. And you might have thought one was easier than the other. But what if I was to give you something like, do I have an example on the next page? Well, that's no fun. Yeah, do this one. Something like this one. Do you want to FOIL this one? Oh, it looks so fun! It's a trinomial. Wouldn't you have to like rainbow it 6 different times?
Yeah.
So 1, 2, 1, 2, 1, 2. Instead, now imagine if you had to do the limit definition. Yeah, f of x plus h. Ooh, that'd be fun. But how do we do product rule? This is Newton's notation now. F prime of x, keeping it with function notation. Second, keep it the same. 7 plus x to the 5th. D first. What's the derivative of? Careful. 2 minus x minus 3x cubed.
Negative 9x.
0.
Plus
Negative 1. Negative 9x squared, right? So, 0 minus 1 minus 9x squared. Second D first plus first. D second. 0 plus. Now, if this was a long answer, what could you do? Stick it to the man and say, ha ha ha! But if it's any sort of multiple choice, you have to try to simplify. Now, the very first thing we ask ourselves, for those that need notation, it was second, D first, plus first, D second. First thing you do is ask yourself, are any factors shared across the plus? Nothing shared. So we can't pull any like big old factors out, like we did with grouping. However, what can we do? Yeah, it's a bummer. But we could distribute. So if you did need to simplify, you would have to go ahead and do things like FOILing the first. Oh, why is it blue? That's important. Negative 7 minus 63 x squared minus x to the 5th minus 9x to the 7th plus 10x to the 4th minus 5x to the 5th minus 15x to the 7th. 10 minus 5, and then we would combine like terms, right?
Yeah.
Okay. So, can the simplifying maybe be harder than the calculus?
Yes.
You just have to take it one step at a time. But I also said, still, even back here, couldn't we have distributed first and then done the old-fashioned, just take the derivative term by term?
Yeah.
We could have rewritten and then taken a derivative. Do you have a choice on this one?
No. Simplify.
You can't distribute, it's signed. So you have a first, and you have a second, and your only option is product rule. Kiddos, let's finish it off. How to take the derivative. Second, who is what? Sine. B first, which is? Plus first. What's the derivative of sine? Cosine. Alright, I'm going to rewrite it to make it a little bit nice. We usually get the trig at the end, but otherwise, I guess you could, not negative. I guess you could factor out a 4x, but I don't know if you need to. Unless you're finding horizontal tangents. Cool kids, we talked about product rule. Tomorrow, motion questions. Finish up that homework. I did a lot of these today. And we have to do quotient rule and practice and compete. Bye, cool kids.
Wait, Miss D.
Pass.
Bottom D top.